So, Moore's law gave us the power of computation. Metcalfe connected us all together with networks so that we could tie into people and data and AI more recently. And what I saw last year was this huge opportunity, this glimmer of what might happen when Moore and Metcalfe meet Mother Nature and some of the wonders coming out of Mother Nature's research labs. I think I'm kind of humbled and excited about this, and I think there's a biomaterial revolution on the horizon. I'm a design scientist. Last year about this time, I attended, and I saw this fairy tale-like wonder about what was going on in Mother Nature's laboratory over maybe 4 or 5, maybe at least 4 billion years. So let me start with a little backstory, how I got here. So 2 years ago, I took a class called How to Make Almost Anything. It's by David Kong and George Church here at MIT. And David connected me to Dr. Fio Omenetto from Tufts at the Silk Lab. I was exploring how architects and designers like me could actually embrace biology. My final project was just a playful idea. What if we could have a MakerBot but a SpiderBot? What if we could actually kind of explore the possibility for architects and designers to prototype stuff quickly using generative design and sort of turn some knobs and learn about what might happen and make something. Architects and designers need to touch stuff. We need to print stuff out. We need to make and feel the materiality. And so Fio said, yeah, I'll help with that. I can supply you with powder and with liquids of silk so that you can build your prototype. But he also said, you should come to this Planet Action thing. I'm going to give a talk. I said, oh, okay, it's a good excuse to come to Boston. And so I got here, and Fio said, look, we've gotten into a ton of problems because of the material choices. We've had many material ages, the Iron Age, the Plastic Age that started, I think, with the Graduate movie in the 60s. But he also shared this fairy tale-like wonder of magic that he was discovering with a group of polymaths around this crazy set of structural proteins. I needed to learn what structural proteins were, too. So what he talked about was I think, pretty interesting. It was a polymathic, polymorphic structural protein. It's an amphiphile. That by itself is kind of an interesting protein. And it's a living material that's evolved in moths on mulberry trees, but it's also evolved in clams in the deep ocean. And he was talking about something that I think we take for granted every day, which is silk, which, if we look on the inside, I've got some silk right here. When I joined Autodesk, my first initiative was really around how we might do generative design and use AI and algorithms and physics simulations to evolve products and places. What we were doing was we were sort of looking at how might you design the negative space, the goals, constraints, the obstacles, the variables of how you manufacture, how you assemble this stuff, how you get performance characteristics, and all those kinds of things, and then how form might follow forces, and how we might actually evolve products in the wild, and the car could join the design team. We were putting sensors over everything. We were putting them in the helmets of the drivers. We were putting them on the road, and then we were taking it out to the Mojave, and we were beating the heck out of these things. And what was really interesting was that this aha moment came to me when we were out in the Mojave Desert with some of the best drivers in the world with these cars, and they were destroying them. And we captured 4 billion data points every afternoon. And then we pumped that back in, and we actually could say, how might it help us co-evolve? There was this feedback loop of living intelligence. We could look across the entire design system, and it would come up with ideas to optimize the system, but also how it might be manufactured, because that might be one of the sliders that we could set. And what we found immediately was that it could co-evolve and actually take sub-assemblies and evolve single assemblies. It could lower the weight. It could increase the performance, and it could be printed on the fly from the cloud, which is kind of interesting because in automotive design, 70% of all the parts that you manufacture, all the spare parts that you have to make for warranty purposes, are never used. So they're sitting in a warehouse for the rest of time, huge amount of energy put into them, huge amount of materiality, and we never use them. Now, just a few weeks ago, a game designer in the UK and a digital biologist at University of Washington won a Nobel Prize for how to actually take DNA, through RNA and predict the folding structures of proteins. Now, this was kind of exciting because it gave me a sense that maybe we've already got all the data we need because of the Human Genome Project to actually do what I want to do, which is generative design for the built world with living materials. There are even new startups that are actually starting to help us query nature and come up with proteins that don't exist in nature, like invent new proteins. And that's kind of exciting. So at this point, I thought this was a done deal. The biomaterial revolution is just going to happen. But I will tell you this, as a product designer and as somebody who's had to make a lot of stuff, the gap between molecular design of proteins and making something that can actually serve a purpose for hundreds, millions, or billions of people around the world is vast. Let me explain this maybe a different way. If you were to put biology at one end of the spectrum and say, okay, how does this work? Life has found a way over billions of years how to assemble perfect atoms into perfect molecules, into perfect systems that are inherently biodegradable. That's kind of exciting. And humanity over the last 200 or 300 years has actually boosted up this industrial revolution. And it's been mostly focused on this sort of idea of how we might industrialize the production of everything, inorganic and organic materials alike. Now, most of it has been focused on assembly. We've largely focused on building stuff, new things, new places. We filled the world with it. We've really not focused on disassembly. I think we haven't focused on it. We just said, we could throw that away. Don't worry about it. Somebody else will deal with it, maybe our next generation. We also focus on centralized manufacturing. Think of Henry Ford and the rise of this optimized supply chain. We optimized for what we thought mattered in that supply chain. Now, nature's way over here. Every cell in your body has a spare copy of you, except for mature red blood cells, in the form of DNA. Nature chose promiscuous replication, massively distributed approaches, and localized manufacturing and production. It's very decentralized. Nature is showing off every day about how we make things and how to take things apart if we would just maybe listen and pay attention. Drew Endy, who's a sort of pioneering digital biologist, he said, trees don't manufacture all their leaves in some central factory, ship them halfway around the world, and staple them onto branches. By the way, fish don't order their spare scales if they lose some scales from, like, Amazon. Okay, kids actually don't have different bones grown at different times of their body and then go into a service center once a month to get the bones swapped out. That all sounds like really bad science fiction. It sounds like a great Hollywood horror movie. But that's not how nature did it. Nature is subtle and has found all these beautiful ways, luckily, I think, to actually do things that Henry Ford could never imagine. Now, human society's done a great job, and they've focused mostly on this sort of industrialized process so that you can make predictable, repeatable units. We take these beautiful trees, and then we pound them down into basically planks, and then we cover them with plasticization so that we can kind of like make sure that they're a nice deck for us. And we destroy all the wonderful variability of life. We also have focused mostly on centralized production. We got to optimize that supply chain. And it's great. We've actually gotten to the point where we have the ability to make just about anything. But we had two assumptions that these are based on. One is that we have an infinite pool of resources. And the other is that we've got infinite oceans, both in our bodies and out in the real oceans, to dump our waste. Nature's way over here. Nature is just everything that it does with materials, with the stuff we're built of. It's all part of this sort of living system on Earth. And life's bioengineers builds things from access to finite resources. Those trees just figure it out right where they are to make those leaves, down at the molecular level. And they've also found a way to disassemble things as well. So it's pretty exciting. And I guess my question, my challenge to all of you is to say, what happens if we could merge what we've learned, because we're pretty smart monkeys, I think that's good, and also what nature's learned, and weave these together and create basically a new material age, a living material age. And so my mission is, how might we take on the challenge of eliminating forever material monocultures and cultivate unexpected variability and wonder in living materials? Now, our lab is already at the point at the Silk Lab of taking regenerated silk fibrine and turning it into a liquid or a powder for novel new uses. It's a commodity at this point. They've done that. We now make thousands of metric tons of it with our manufacturing partners. And we've gone from farms to future. But we're also working on going from waste to wonder, because it turns out silk can be recycled in wild ways. And so that's kind of exciting too. And I'll give you an example. 11 million tons of silk waste pile up every year. And we can take that silk waste with some salts, some agitation, a little heat, actually safe salts, agitation, a little heat, low energy, and suddenly make paper out of it again. Paper that won't catch on fire, actually. We can also build new kinds of things. This is a leather printer that can actually take silk and cellulose from agricultural waste and chitosan from shrimp shell waste and actually create a form that we've never had before. We can also take and create new kinds of foams and composites. So this is formaldehyde-free particle board made from wood chip waste and silk. And we're finding that actually you could use silk. It's an amphiphile. Go look that one up. It's kind of an interesting word. We can use silk to reduce a lot of the toxic chemicals in microelectronic manufacturing and start to develop new ways of sensing all of the things in our lives and doing sort of biology to digital conversion. We've also got water-dissolvable, totally safe. Silk has been used for thousands of years as stitches, ways of making electronic circuits that could send signals. And so that's kind of exciting as well, and it gives us a hint at what's possible. And then we can have cancer-sensing undergarments that are just basically silk-screened, and they're able to actually detect what's coming off our bodies in terms of proteins that might signal that we've got cancer. Or we might be able to actually just silkscreen a whole bunch of shirts and jerseys in a basketball court and be able to en masse detect what's happening in human health and detect new kinds of signals beyond just pH so that we could think about how to close the loop and maybe have personalized printable vitamins. So there's something interesting going on here. And if you think about it, nature embraces dynamic functional variability. Life is ultimately a big data system. And it's continuously emitting and detecting signals, and it's shaping itself to the environment, and it's shaping us. And it's this glorious embodied cognition, embodied intelligence. And it goes from cells to cephalopods to all the crowds here in this room today. And so that's what we could tap into if we could start to listen. Now, I just talked about one protein. There are 300 million proteins in the world. Now, all of them are not going to be wonderful, amazing, like keystone proteins like silk. And frankly, we don't have enough PHIOs in the world and enough time to have the kind of polymorphic, polymathic labs that I've seen where people are deeply interdisciplinary and collaborative and play. But we could maybe encourage the next generation if we could build better tools, if we could democratize the tools. And so that's what I get excited about. I think we need a global unexpected material surprise movement. And I want to end on a grand challenge. Here's this opportunity for us to think about as we're building a living material age. AI is accelerating what's happening down at the lowest level for proteins, down at the nano level. But we don't today have a way to actually synthesize and predict what happens at the meso or the macro level. We don't have a way to do that for individual proteins like just silk stuff, but also for these weird new hybrid composites. And we don't have a way to predict how to actually not only assemble it, but disassemble the stuff as well and find that hidden wonder. And so this is a grand challenge. It might take what it took to do the Human Genome Project to do this, but it could democratize this. It could let us have Tinkercad for 6-year-olds, but actually with structural proteins, where we could actually play, and we could inspire fairy tale-like wonder. So I want you to decide if you're going to join us. I want you to join us, whether it's joining the team, whether it's helping us build a global movement, but we've got to do this. Thank you.